Alrighty, here we go. Le Chatelier's principle. It's one of my favorite parts of this unit. It's kind of, you got to wrap your brain around it and kind of think about how things are working, but I think it's a lot of fun. Think back to our escalator example with you walking up a downward moving escalator. With the rate of the moving stairs and your walking evenly matched, you appear to be at a standstill. But what happens if the escalator begins moving just a little faster? If you want to maintain the same position you had at some specific point between the bottom and the top of the stairs, you'll also need to make some adjustments. Chemical systems at equilibrium tend to make these adjustments as well. A French chemist, Henri Louis Le Chatelier, was the first to describe what we now call Le Chatelier's principle. If a system at equilibrium is subjected to external stresses, the equilibrium will shift to minimize the effect of that stress. Equilibrium rates. Equilibrium is all about rates. The rates of the forward reaction is equal to the rate of the reverse reaction. External stresses are factors which will cause the rate of either the forward or reverse reaction to change, throwing the system out of balance. Le Chatelier's principle allows us to predict how this will affect our system. In our unit on kinetics, we examined factors that influence reaction rates. Recall these factors. You would have looked at this in grade 10. So concentration, pressure and volume, temperature, and catalysts. We will see how changing these factors affect a system of equilibrium. So we're going to start by looking at changes in concentration. So let's consider this following reaction. So Fe3- plus SCN- gives us FeSCN2+. If more Fe3+ is added to the reaction, what will happen? So according to Le Chatelier's principle, this system will react to minimize the stress. Since Fe3+ is on the reactant side of the reaction, the rate of the forward reaction will increase in order to use it up. To use up the additional reactants. This will cause the equilibrium to shift to the right, producing more FeSCN. For this particular reaction, we will be able to see this happening as the solution will become a dark red color. There are a few different ways we can say what happened here when we added more Fe3+. These all mean the same thing. So we could say the equilibrium has shifted to the right, the equilibrium has shifted to the product side, or the forward reaction is being favored. So the concentrations of the participants, the reaction participants. So how does this cause the concentration of the reactions participants to change? So the Fe3+, how is its concentration going to change? Let me just write out this equation here. Alright, so since this is what we added, this concentration goes up. Alright, so we're going to go up here. So with our shorthand, we could write the concentration of Fe increases. The equilibrium shifts to the right, so it shifts this way, which means more of the reactants are going to be used up. Since the SCN is a reactant, it's going to end up decreasing as the rate of the forward reaction increases. The FeSCN2+, because the forward reaction is increasing, we're going to see more of those products, so that's going to increase. So how does the change of concentration affect the key equilibrium? Notice that the concentration of some reactant participants have increased while others have decreased. Once equilibrium is re-established, the value of the K equilibrium will be unchanged. The value of KEQ does not change when the concentration causes a shift in the equilibrium. So what if we added more of the FeSCN2+? Again, the equilibrium will shift to use up the added substance. In this case, equilibrium will shift to favor the reverse reaction. Since the reverse reaction will use up the additional FeSCN. So we could say that in 3 different ways. Equilibrium shifts to the left, equilibrium shifts to the reactants, or the reverse reaction is favored. Alright, so how are the concentrations going to change? So we've added this, so that's going to increase. The reaction is going to move to the right, to the left, the reactant side. So that means that these are also going to increase because the FeSCN is going to be reacting to form the Fe3+ and the SCN-. So what happens if we remove concentration? So sometimes this happens if we add something that's going to create a different chemical reaction and remove some of those molecules from the system. So what if we remove the SCN? So let's remove some of the SCN, perhaps by adding some lead ions. The lead 2 ions will form a precipitate with the SCN, removing them from the solution. What will happen now? The equilibrium will shift to replace the SCN, and the reverse reaction will be favored because that direction will produce more of the SCN. So we could say 3 ways again: the equilibrium shifts to the left, the equilibrium shifts to the reactant side, or the reverse reaction is favored. So the concentration can also be changed by removing the substance of the reaction. This is often accomplished by adding another substance that reacts in a side reaction with something already in the reaction. So because we've removed the SCN, so we initially remove it, that concentration goes down. That makes the reaction want to go this way to replace it. So that means this concentration is going to go up, this concentration is going to go up, this concentration ends up going down. It says this needed to be changed, so this should be going down. I think your notes are right, but it needs to be changed. Changes in volume and pressure. Changing the pressure or volume of a container enclosing an equilibrium system will only affect the reaction if gases are present. You may remember in earlier chemistry classes that equal volumes of gases contain an equal number of particles, and under standard conditions of temperature and pressure, STP, 1 mole of gas occupies a volume of 22.4 liters. This is known as the molar volume of gas. So 2 moles of any gas will occupy a volume of 44.8 liters, and half a mole will occupy 11.2 liters. How does changing the pressure and volume affect equilibrium systems? If you increase the pressure of a system at equilibrium, typically by reducing the volume of the contents, the stress will best be reduced by the reaction favoring the side with the fewest moles of gas, since fewer moles will occupy the smallest volume. Conversely, if you decrease the pressure by increasing the volume of the container, equilibrium will shift to favor the side with the most moles of gas, since more moles will occupy a greater volume. If both sides of the equation have the same number of moles of gas, then there will be no change of the position of the equilibrium. When considering the effect of changing volumes or pressures on equilibrium systems, we be sure to only count the number of moles of gases on each side of the equation. Solids, liquids, and aqueous solutions will not be affected by the change in pressure and volume. So here's an example. Predict the effect on the equilibrium when pressure is increased for the following reaction. So we have the dinitrogen tetraoxide giving us 2 moles of nitrogen dioxide. So there's gas on both sides of the reaction. There's 2 moles over here and only 1 mole over here. So we are increasing the pressure. So that means that the reaction will want to move over to the side with the fewest number of moles, because the fewer number of moles will fit into a smaller size container. So that means our reaction is going to go to the left, or the products are going to be favored, which means that the concentration of this will be increased. All right, changes in temperature. When temperature is the stress that affects the system at equilibrium, there are 2 important consequences. An increase in temperature will favor the direction that absorbs heat, so the endothermic reaction. Remember, heat is entering a system in an endothermic reaction. And the value of the K equilibrium will change. So here's an example. Consider this a reaction. We've looked at it already. So the N2O4 reacts to give 2NO2 with the delta H of positive 56.0 kilojoules. So that means the forward reaction is the endothermic reaction, and the side that's going to absorb the heat. Okay, so that means the forward reaction is going to be favored, and so the reaction is going to shift this way, which means the concentration of this will increase. So why will the K equilibrium change when it did not change for concentration, pressure, and volume? When the temperature changes, causing the equilibrium to shift, one entire side of the reaction equation is favored over the other. Mathematically, this will alter the K equilibrium as follows. So K equilibrium, remember, is products divided by reactants. If the forward reaction is favored more than the products are produced, fewer reactants, so the K equilibrium will increase. If the reverse reaction is favored, there's fewer products and more reactants, the K equilibrium will decrease. So in our example given on the previous slide, increasing the temperature will favor the forward direction and the K equilibrium will increase. Removing heat, or making the system colder, will favor the exothermic. The exothermic reaction releases heat into the surroundings, thus replacing the heat is being removed. So the addition of a catalyst. Remember, a catalyst is just another chemical being added that speeds up a reaction. The addition of a catalyst to an equilibrium system is the final factor that we're going to be looking at. So we're looking at nitrogen and oxygen gas being combined to form nitrogen oxide. The addition of a catalyst to this, or any other equilibrium system, will not affect the position of the equilibrium. A catalyst speeds up both forward and reverse reaction, and there is no uneven change in the reaction rate. Generally, a catalyst will help a reaction reach a point of equilibrium sooner, but will not affect the equilibrium otherwise. Alright, so there's your lesson for the day. See you in class tomorrow, where we will look at some examples and do some questions on how the Chatelier's principle will affect different systems.